Yes. So we can say that a quantity of information is something which is inversely proportional to the probability. Something which is rare, when it happens, brings more information. So the quantity of information is 1 over P1, 1 over Pk. This is E1 and Pk. And now, if two events has to occur, the probabilities, and if the events are independent, the probabilities are multiplied. Okay? Multiplication is more difficult. If you take the logarithm, you know that the origin of the logarithm is, because the people didn't want to do multiplication, they invented logarithm to transform multiplication to addition. Logarithm of A and B is logarithm of A plus logarithm of B. So, in place of using this, we are going to take logarithm. Taking the logarithm makes that the quantity of information is going to be additive. Additivity. We are going to define the quantity of information not 1 over P, but minus log P. Logarithm of 1 over P minus log P. And in this case, if I have two events, the quantity of information will be additive. So I have defined what is the quantity of information. And now the entropy is just the mean value of quantity of information. So the entropy, H, is just the mean value. Mean value is sum over Pk minus log of Pk. And this is the definition of entropy. The mean value, the expected value of information. Okay, so this is a definition of entropy for discrete case. We can extend it very easily to the continuous case. And for the continuous case, we have the definition of entropy and the definition of entropy for the continuous case is integral of minus integral of minus sum becomes integral of P of x logarithm of P of x. So this is the entropy. And now, principle of maximum entropy. Principle of maximum entropy says that if you do not know, if the only information that you have is the mean value and the variance, you have a lot of choices. Choose the probability distribution which maximizes the mean value of information. Mean maximizes entropy. So the principle of maximum entropy is just so the principle of maximum entropy is choose probability distribution P of x in such a way that it maximizes entropy. So the mathematical problem is maximize minus integral of p of x logarithm of p of x, okay, subject to what you know. And what we know is, for example, these two. I am going to combine this and write the expected value of pk of x to be equal to pk. P1 is x, P2 is this. I may generalize if I had more piece of information. And this problem, this mathematical problem, we had it before. Maximizing something subject to something subject. You can use the technique of Lagrange multiplier, and we can obtain the solution for the problem. I'm not going to go more in details of this. And what is just interesting is that if you only know the mean value and the values and use this principle, you obtain that the solution, the maximum entropy solution will be that x is a normal distribution. The word normal, because the question is that why the Gaussian distribution, people have called it normal. Normal is that it is the simplest. It is the maximum entropy solution, knowing only the mean and the standard deviation. And it has many other properties. It is symmetric. All the estimators are the same, and so on and so on. There are a lot of properties for this Gaussian distribution, which is the simplest, which is the more general, which has a lot of properties. That is why the people call it normal distribution. So let's go back. What was the question? The origin? The question was, we wanted to assign a prior probability to theta. For if I knew something about theta, I could use this principle of maximum. But very often this is not the case. Even the mean value I may not know. But for example, I may know that, okay, it can take any value, either positive or negative. That's all. Or it has to be positive. So the quantity of information that I have about the theta may not even be this. Because this is a particular example that I showed you. If it was the case, we could use principle of maximum entropy. But if not, we use what is called, say, conjugate priors, reference priors, non-informative priors, and there has been written many books, and one of the books is Bernardo's books, and there is a conference which occurs every 4 years in Valencia in Spain, who still the people talk about how to define priors. There are many techniques. I am just going to tell you about conjugate priors. Okay. And we are going to stop here. Let me. So we talked about maximum entropy, There are a lot still to tell about entropy and maximum entropy, but this is not, this could be a course by himself about talking about entropy. If you all, I can talk about that, but this is not our main objective. So let me talk about the conjugate priors, and this we are going to finish this morning. Conjugate prior. I write again the base rule. Conjugate priors is just a tool. Just because the people have proposed this to simplify the computation. Okay? So we are not going to discuss a lot about the choice of the priors. This is not the matter of this course. We are talking about inverse problem. So I am just giving you the tool, the way that we do, and this is just a simplification tool which helps us to do the computation easy. Okay? So the conjugate prior, the idea is that, okay, I have to choose the prior to be able to apply the base rule. Okay? And I do not know what to do. One idea which is interesting is that, okay, because you do not know what to do, choose this prior in a family. Choose this prior in a family, which may depend again on the hyperparameter. We have parameter, we have observation, and we have hyperparameter. But how to choose this prior, how to choose this family in such a way that when we apply the base rule, and we obtain the posterior probability, this posterior probability be also a member of the same family. Apostolic. So this will be helpful, this will be easy then to apply and to use it. It means that if I do this, the things will go very easily. I choose the prior probability, which depends on some hyperparameter. When I apply the base rule, I obtain another posterior probability. But I know that if I can do that, I know that this posterior probability is in the same family. So what? So just I have to update the parameters. And so this makes the things easy. So choosing this, the problem becomes the base rule becomes updating parameters, updating hyperparameters. Let me give you an example that we will use in practice. Let's assume that xi follow a Gaussian distribution. Okay? So these are the parameters. First, I am going to assume that I know the variance, I do not know n. So the only unknown parameter is theta. Variance I know, just to simplify. So the question is, I have observed x1, xn, and my question is, what is theta? I want to do Bayesian ratio. So I write probability of theta given x, which is, I'm going to use this expression. This means proportional to. Because this denominator does not depend on theta, I can ignore it or not. So this will be probability of x theta, probability of theta, and here I am going to use a prior probability in the conjugate prior. So this theta will depend on some theta 0. And now what I would like to do is that choose this in such a way that this and this be in the same family. Okay? If I can do that, it will be easy to do. We can show that if the likelihood is Gaussian, this is the case that we assume here, and if the parameter of interest is the position parameter, this is the scale parameter, this is the position parameter. Here I assume that the scale parameter is known, this is the position parameter. So it is easy to show that because this is Gaussian. If I choose this also Gaussian, so it means that I'm going to choose it to be Gaussian, which means that M0 and say a variance between V and V0, say. Then this is Gaussian, the product of two Gaussians is a Gaussian. So I will know that this will be a Gaussian. So because this is Gaussian, if I choose this Gaussian, the product of two Gaussian will be again a Gaussian. And in this case, it is very easy to show this. And so we can say that when the likelihood is Gaussian and when the parameter of interest is a position parameter, then the conjugate prior will be a Gaussian. This is the conclusion of it. Now, how about this case? If the parameter of interest was not M but V, then I can show, you can do it as an exercise, that in this case, for V, let me write it V directly. For the prior that you have chosen is inverse gamma that you have to choose. Gamma distribution, you know, inverse gamma distribution gamma, no, I have. If you have a gamma distribution and you change a variable of x to 1 over x, you obtain what is called inverse. And then inverse gamma multiplied by a Gaussian again gives an inverse gamma. So we say that if the likelihood is Gaussian, and if we choose an inverse gamma for the scale parameter, then the posterior probability again will be inverse gamma. Only the parameters will be, here we will have a Gaussian with theta, with the parameters which becomes m a posteriori and v a posteriori. And here we will have an inverse gamma with the parameters which become alpha a posteriori and beta posteriori. This would be a very good exercise to do for you. Just take a little time, do this operation, and show that this is really Gaussian. Take an inverse gamma, multiplied by Gaussian, and show that the result is inverse gamma. Do we have enough time? 2 minutes? Okay. So let's just summarize. The next time we will apply this Bayesian approach for the inverse problems. But today, actually, I tried to give you all the ingredients that you needed to be able tomorrow to apply the Bayesian approach to inverse problems. So, what was the main point? We talked about parameter estimation. We talked about likelihood and transfer of maximum likelihood. We talked about Bayesian approach, the main idea. We talked about how to do inference from the posterior, how to do the inference. We talked about cost function and decision theory, which tries to optimize the expected value of cost function. And we saw that with different expression of the cost function, we can obtain different estimators, different point estimators, expected value, median, or mode. And we discussed one of the two rules, how to assign a prior. To assign a prior, either we know something in the form of expected value, then we can use principle of maximum entropy, and we just define entropy very simply. What is the definition of entropy? We can apply the principle of maximum entropy. And finally, we say that, okay, what if we do not even have this? Just we do not have this information, then a tool which simplifies the way of doing the computation was the conjugate prior. The conjugate prior, the idea is that if I am going to choose to simplify my life doing the computation, choosing a prior in such a way that the posterior stays in the same family. And two examples which are very